So this is my review for the atomic structure section of the ACS. I want to remind you first off that this is not a comprehensive review. My goal is to try to go over a few of the areas we did in class to try to refresh you on some ideas, but that this is not going to cover absolutely everything that will be on the exam necessarily. I can't cram in all of a couple weeks, a week or two of class into like 30 minutes. But this is to try to cover a few of the things you may have forgotten, hopefully make them feel more familiar. I still suggest you review these sections of your ACS review guide, but here's some additional questions that may help out some. I also want to suggest that for each slide, you pause before I go through the questions and actually try answering them first. There are a few facts, but mostly these are questions. That'll give you an idea of which questions do you already remember and which ones make you go, wait, I'm going to need some help. Because once I've said them, that specific question will look really familiar, but it may be that you don't actually remember that idea all that well. So that will help you by trying to solve the problems first to see if you need to go back and look at that area more carefully or not. So let's start with atomic symbols and subatomic particles. So to be able to talk about atoms, we're going to need to know a few things. First off, we need to remember that there are 3 subatomic particles. Remember, we have the neutrons. Those have mass, and they're in the nucleus, and they have a neutral charge. That means they don't contribute either positive or negative to the overall charge of the atom. We then have protons. Those also have a fair bit of mass. They're also located in the center of our atom, in our nucleus. We then have electrons, which have a negative charge. So they're the opposite charge of the proton, and they tend to have a whole lot less mass. This doesn't mean that it's a mass of 0, but we don't end up counting them when we do things like mass number because they're so much smaller than the protons and neutrons. So we don't always have neutral atoms, though. If we have an atom that has lost some electrons, it becomes what we call a cation. So we'll represent these with a positive charge, like maybe a +1 or a +2, designating how many electrons it's lost compared to how many protons it has. Similarly, anions are when an atom is going to have more electrons than protons, creating a net negative charge. So it gains some electrons. So maybe we have a -1 if there's 1 electron more than the number of protons. Or we'll have 3 more electrons, it'll be -3. What you'll notice in both of these cases is I mentioned the fact that the electrons are what's changing. We're not changing the number of protons in the nucleus. If we did, it would become a new atom. Instead, when we're creating ions, we're changing the number of electrons by either taking them away or adding additional ones. To be able to talk about atoms then, we're going to need to be able to have some type of symbol to represent this. So below I've got a few different symbols we could use that we should be able to go back through and be able to designate how many neutrons, electrons, and protons there are in each of these systems. So we'll start here with this symbol here, 2H1. So what we should know is that hydrogen is going to have 1 proton. We can get that from this number down here. In addition, we can get it by looking at our periodic table and seeing that hydrogen does indeed have 1 proton. We know that because there is no symbol up here in the corner, that this is neutral. That means that the protons have to equal the electrons. So we have 1 proton and 1 electron. Finally, to find the neutrons, we're going to have to go to our top left number. Our top left number is called our mass number. That is the number of protons and neutrons we have together. So we take the mass number, subtract our atomic number, and we're left with how many neutrons we have. So this system has 1 proton, 1 electron, 1 neutron. Let's look at 2 more examples. So here we have calcium, and we can see from our numbers that we have 20 protons. That's in the bottom left. Again, we don't have a charge on this calcium, so we're going to have 20 electrons. And then we'll get that we have 20 neutrons. This comes from our mass number of 40 minus our 20 protons. It's important to note that the number of protons and neutrons are not always necessarily the same. We'll see this in our 3rd example. So here we have 56, iron 56. So here, because there's 26 in the corner, we know we have 26 protons. We also know because it's neutral, there's nothing in the upper right, we have 26 electrons. We then need to find the number of neutrons. which is going to be equal to our mass number of 56 minus our 26 protons. In this case, we have 30 neutrons. So in this case, we have a system where the neutrons don't equal our number of protons. So I'm going to make sure to check that it'll not always just be that they're exactly the same. There's one more thing I'd like to look at with this terminology that I don't have an example of here. Let's say instead of writing it like this, I had given you something that looked like this. And I asked you, what is X? So in this case, X is a way to represent an unknown atom, and you'd probably have 4 choices to come from. In this case, you should be able to identify the fact that there is a 2 here, means that this is going to be helium, because we go to our periodic table, and the atomic number 2 corresponds to helium. That means this is going to be the helium atom. We could also be asked other questions, such as how many protons would there be? There would be 2 protons. Also, because it doesn't have a charge, there would be 2 electrons. And again, there would be 2 neutrons here, because we would have 4 for our mass number minus our 2 protons. So you should also be able to identify an atom if it doesn't give you the symbol for it, by using the information from the number of protons, neutrons, and electrons. That could be either represented like it does here, where I give you a symbol and then just put an X there, or the problem could simply tell you something like you have 3 protons, you have 3 electrons, and you have 2 neutrons. What atom do you have? And then you should be able to figure out from that, oh, if I had 3 protons, then I would clearly have to have lithium. And because there are 3 electrons, it would be neutral, so it wouldn't be an ion. So you should be able to figure that out no matter what way this happens to be written. So far, though, we've always looked at things where the atomic number is given, but that won't always be the case. So for our next 2 examples, we have 25 mg. Here, you'll notice there's no number written here. That's because since you have the symbol, we know you can actually find that out. So if we go to our periodic table, we find out that magnesium has 12 protons. We can then check, and because the mass number is 25, we're going to know there are 13 neutrons. That comes from 25 minus 12. And then we also know there are 12 electrons because this one is neutral. No symbol up here. You may notice so far I've just dealt with neutral systems. So let's look at something that's not neutral. Here we have potassium 39. But this time it has a plus charge. So we'll go through and do the 2 that we know. Our protons for potassium are always going to be equal to 19. Note that when you look this up in the periodic table, it says 19. You don't add an extra proton because of that positive charge. If you were to add another proton, this would become calcium. So that plus charge, even though protons are positively charged, is not what changes in our system. Then we can also find that our neutrons, which are unaffected by the charge, are equal to 20, and that comes from just 39 minus 19 protons. So then we have to find the number of electrons. If this had been neutral, we would simply write that it was 19. But in this case, we have to take into account the charge. So in this case, we have 19 minus 1. Because there's a positive charge, that means there are fewer electrons. You'll notice I am subtracting, even though it's positive. It's important to pay attention to the sign. There are 18 electrons in our system and 19 protons. That's because that gives it a positive charge overall, as there are more protons than electrons. Similarly, if we were to have a system that was an anion, let's look at one of those. So let's say we had chlorine minus. We'll make it chlorine 35. Here we can look up, and the number of protons in chlorine would be equal to 17. But here, if I want to find the electrons, even though it's negative, we're going to add, because that gives us an additional electron, which will give us a higher negative charge. So 35 Cl minus will have 18 electrons. In addition, you could remember that if there had been a number in front of the charge, you would have added that number instead. For example, if you had had sulfur 2 minus, you would have added a 2 instead of a 1. So just add whatever big the negative charge is, or if it's a positive charge, you'll subtract that number. We then still solve the neutrons the same way. We have 35 minus 17. So this is going to have 18 neutrons. So that tells us the 35 chlorine minus anion is going to have 17 protons, 18 electrons, and 18 neutrons. So let's use this information now about things like calculating electrons and try the last question. Which pair of these four sets of atoms and ions has the same number of electrons? In parentheses, I put the word isoelectronic. This is because if they asked you if it was isoelectronic, this is actually the same question, but it uses a different word, so you should be okay with both terminologies. So here, let's start with part A. In A, we have both sodium plus and lithium plus. Well, if I figure this out, sodium plus is going to have 10 electrons, but lithium is only going to have 2. So even though they're in the same column, that doesn't have anything to do with them having the same number of electrons. So then we get to the next one, potassium plus and Br minus. You'll notice that even though they're in the same row, that isn't related to the fact they have the same number of electrons in any way. So if I look at potassium plus, let me find my cursor. My cursor disappeared. There we go. So potassium plus is going to have 18 electrons, while bromine minus is going to have 36 electrons. Clearly, this isn't a good answer. We then get to C, we have neon and argon. Well, neon has 10 electrons, while argon is going to have 18. That's going to make it a no-go. They are both noble gases, but they have different numbers of electrons. Then we get to D. Hopefully this works out. So our fluorine minus is going to have 10 electrons. That's because fluorine has 9, and we have 1 extra for the negative charge. We then have sodium plus. It's also going to have 10 electrons, because it starts with 11, and then it loses 1 to become a positively charged cation. Therefore, our answer is D. Fluorine minus and Na plus have the same number of electrons. Now, why don't you try a couple of these on the valence electron configurations? So first, we'll try one where we have to actually come up with an electron configuration. So, what is the electron configuration for chlorine? So, remember, we have to, if you don't remember the order for how you fill up all the orbitals, I strongly encourage you to go back and use whatever particular memory technique you like to use, whether it was that drawing with arrows, or if you just memorize them in order, or if you look at the periodic table and remember the blocks they're in. Whatever works for you, go back and make sure you can remember how to remember the order of the electron arrangement. You can also go back to my notes or go back to your textbook. It has some reminders about that as well. So we know chlorine is going to have a total of 17 electrons. So when we're writing these, we better get up to 17 total. So we'll start with where the first electrons go. We know 1s2 is our first sublevel that's going to get filled. That gives us 2 electrons. We know next is 2s2. This is followed by 2p6. So far we have 10 electrons, so we're going to need another 7 to go. So next we're going to have 3s2. 3s2 will get us to 6, 8, 10, 12. We need 5 more. So the last energy level is going to fill us up. And remember, to take into account how many you have left over. Chlorine doesn't fill up all the way, so if you put 3p6, that wouldn't be right. So we're only have enough electrons to fill our p to the 3p5. So this is our electron configuration for chlorine. Note that if the question had asked for chlorine minus, you would have add to an extra electron and it would have been 3p6 instead of 3p5. So make sure you pay attention to things like signs on your species. So you could have chlorine neutral, like you do here, or you could have chlorine minus, where the answer would then be a little different. So let's try going in the reverse direction. Which atom has the ground state electron arrangement 1s2, 2s2, 2p6, 3s1? First to note, the term ground state is only given to say that it's not excited and you don't have electrons in some different energy level than they normally would be. So that's the electron configurations we were learning in class. We weren't worried about what if one electron is temporarily somewhere different than normal. So if we go, we can see that we have a total of 2, 4, 10, 11 electrons. And if I follow along my periodic table, I notice that as I do that, my 1s2, 2s2, 2p6, when I get to 3s1, if I'm counting along that way, I get to sodium, which is going to be Na. So for this is just practicing going along your periodic table and seeing when you get enough electrons for that. The more challenging questions in this area will usually, instead of asking which atom, which tells you it's neutral, ask you something like which species. And then you would have to check all of the possible right answers to see, are some of these ions? Would that add or subtract? You would also need to take into account the fact that means that there might be multiple answers that you could be looking for, so you need to find the one that matches with that particular state. because we could have multiple things that look like, for example, 1s2, 2s2, 2p6. This particular configuration is the configuration for neon, but it's also the configuration for Na+ or F-. You could even have a question that says which of these does not have this electron configuration, where 3 of them do and 1 of them doesn't. So just be okay with the idea of you're going to have to be able to add or subtract electrons based on if something is an anion or a cation. So let's try one last one on this page. Which of these could be the ground state for the valence electrons of nitrogen? So you may have figured out, if you just look at the answer, you'll probably get this, but in case it wasn't there, first we have to figure out, okay, what energy level is this? So this is our p energy level because it's got three orbitals, where if it were s, it would just be 1 orbital. And we also know that nitrogen is going to have 3 electrons in its p orbital. So all 4 answers do indeed have 3 in the p orbital. But if one of them had 5 instead, which is the total number of valence electrons, it wouldn't be right, because 2 of those should be in the s subshell. So then we've got to start to rule out answers. So first the question is that how do you initially pair up electrons? Is it like A and B, where they start up grouped together? Or is it like C and D, where they're all separated? If we remember our rules, we know that C and D is the correct way to look at it, because all the electrons are going to try to find different orbitals to fill up before they start pairing together. We then have to figure out which of C and D is correct. If you remember, all of the electrons are going to arrange themselves when they're unpaired so that they're facing the same type of spin orbital. So either all up or all down. So C is going to be my correct answer. And don't forget, once you do start pairing them, if it were something with more valence electrons, the second electron has to be going the opposite direction. You can't have 2 going the same direction inside a single orbital. Now just 2 more questions on electron configurations and quantum numbers. Let's give this a try. Hopefully you tried to solve these 2 on your own first. Let's try this one. How many unpaired electrons are there in oxygen in the ground state? So first, so how do I know what it's really asking? Well, what this question wants us to do is we've got to first figure out just how many valence electrons there are and what that orbital would look like. By basically drawing the orbitals we did on that last slide for nitrogen, if we draw those for oxygen, what the correct one is, then we can answer the question of how many unpaired electrons are there. So for oxygen, we know that the valence electrons we're going to be worried about are in the 2p. If you'd drawn the 2s, that would be okay, but you'd notice that they're all paired up. So that's not a word. So oxygen has 4 electrons in the p orbital because its electron configuration is 1s2, 2s2, 2p4. So if we've got to put 4 electrons, we start with 3 going the same direction. They start off unpaired. And the 4th one is going to have to find a home with an orbital that already has an electron because there aren't any open spaces left. This leaves us with a total of 2 unpaired electrons here and here. So it'd be whatever version of the answer said there were 2 unpaired electrons. Now for our last one. I'll also remind you that while we're only asking 1 question about this is a good thing. You might want to go back and check your rules for which quantum numbers are allowed to help remind how to solve problems like this. So which is an allowed set of quantum numbers for n is equal to 3? So let's go through all our rules. So first we know that n has to be equal to a positive integer. So we're okay for this one, but n can't be 0, right? There's no 0 orbital, and n can't be negative. So any options, in any problem, there was something like n equals -1 would be incorrect. So now we've got to remember, what are our rules for L? Our L value is going to be values starting at 0 and going all the way till you get to n minus 1. Or sorry. Yes. Took me a second. I was thinking of a different number for a second. So remember, let's take the s orbital. We know there's only the 1s orbital. And that's because the 1s orbital corresponds to an n of 1 and an L of 0. So the 4 L's, you'll want to remember what they stand for. 0 is an s orbital. 1 is a p orbital. 2 is a d orbital. And 3 is an f orbital. So while you don't have to know it for this question, it's reasonably likely you might for something else. So those are the main L's you're going to deal with. L's can be higher than 3. And if one of those is a possible answer, that's okay to go with. We don't have anything that's like that in the ground state in our periodic table, but that doesn't mean that it's theoretically impossible to happen, which is the goal here, to figure out what would be allowed at all, because some numbers aren't going to be okay. For example, L is not going to be equal to 2 when n equals 1. That just can't happen. So far, these first two rules have eliminated some of our possible answers. A is already eliminated. We can't have an L equal to 3 when n equals 3. So we can get rid of A. That also gets rid of D. So we're left with B and C. So let's look at our next number. We then have m sub L, and m sub L can have values equal to negative L all the way to L, going along one at a time. So for example, if L were equal to 2, m sub L could be negative 2, negative 1, 0, 1, and 2. In this case, this tells us that if L, this helps us eliminate one of our answers. B has an L equal to 1, which is perfectly fine, but then m sub L falls out of the range of the possible answers. So we're going to eliminate B because m sub L cannot be equal to negative 2 when L equals 1. While we know the answer is C, I'll go over the last one just to make sure you're okay with it. M sub S can have two values, minus 1/2 or plus 1/2, corresponding to spin down and spin up. So if D had had an OK L value, it would still be incorrect because m sub S can't be equal to positive 1. So this tells us that our answer is C. For an n equal to 3, we could have an L equal to 2, an m sub L equal to minus 2, and an m sub S equal to plus 1/2, and that would be a perfectly fine set of quantum numbers. So you should be